Hi, it's time for another math easy solution. Today I'm going to go over a video on blockchain technology, and yeah, it's been a while, I think a couple of years since I've made one specifically on blockchain. In this video I'm going to go over the big picture and look at part one, which is going to be on just focusing on the question, what do you own? Question mark. And basically I was going to do this on one part, but I'll do part two in a later times just because it's getting a bit extensive. So anyways, let's go further. So like always, if you don't have time to watch the whole video, you can play this video at a faster speed. You can also skip to the end for a summary. I have a just tiny brief summary there, but not like my usual summaries. This one is just pretty much brings it all together. And you can play this video at a faster speed. And there's my recommendation. This browser extension. Also see my tutorial on that. And that's, yeah, it's a pretty genius life hack. So anyways. You could also download and read the notes. Link will be in the description below, as well as viewing these notes on the Hive blockchain. And you can also watch these videos in parts, and I'll include the timestamps of all the parts in the description. So you can just go and click at whichever section or part or topic that you are interested in seeing. Anyways, let's jump right in. So topics to cover. So recap on my earlier blockchain videos. I go over introduction, note on part one, and the question, what do you own? The numbers on your bank account, your entire digital existence. Then go over the internet, which are cables, which is pretty much just cables of light. Go World Wide Web, language of light, decentralization of information. And then go over decentralization of information, but not of value. And the question, what is value? Physical and mathematical one-way functions, physical boxes, and cryptographic hash functions. Digital keys, passwords, and cryptography. Digital signatures. And then go over the numbers on your bank account again. And then ask the question, whose ledger is it anyway? Where are the ledgers located? Value is a collective belief of a network. And then look at trust, a chain of signatures, copy and paste, and double spending. Chain of digital signatures, consensus is everything. And then look at digital gold, consensus via mathematical work. Digital governance, consensus via network stake. And then variations in digital consensus. And then look at decentralized consensus, everywhere and nowhere. It's pretty much a mini summary of everything that I covered. And then basically last point is digital countries. I want to bring that up because that's where we're heading. So recap on my earlier blockchain videos. So I had made 3 tutorials on blockchain technology, while the 4th video was indirectly about blockchain, since it was in regard to the Brave browser, which just so happens to use the basic attention token or BAT cryptocurrency. And my earlier videos can be seen in the following playlist. Here's a link on YouTube, and there's a short link, mes.fm/blockchain-playlist. Yeah, but in the video notes in the Hive blockchain, I'll include links to watching it on BitChute, 3Speak, and DTube as well. Yeah, so here is the screenshot of the playlist so far. So I went over initially on Steemit overview, social media platform on Steem blockchain, then looked at Steemit tutorial, Steem Power, Steem dollars, and then looked at blockchain overview, Bitcoin, cryptocurrency, cryptography, and Satoshi Nakamoto. And then this video is pretty recent, as custom browser user scripts unlock Brave browser from archive.is. And yeah, this is my blockchain tutorials playlist, and this description is pretty interesting here. I'll just make it bigger here, just copy and paste it in, and let's read it out loud. So the internet brought about decentralization of information. Blockchain provides verification of information. The combination yields the internet a value in which money and ownership flows like information. Follow along my blockchain tutorial series. Understand this major shift humanity is undergoing. And yeah, so I should have just read it from here. But anyways, very interesting. I have a short URL, mes.fm/blockchain-playlist. And yeah, just bigger screenshot of the videos there. And then here's the old archive. I had a different description beforehand, and it was a different setup like this. This is included for reference. The world is going on the cryptocurrency and blockchain route for better or worse. So better understand just what it is by following along this very detailed breakdown on all things blockchain, and in particular Steem, which is my favorite blockchain, etc. Well, it was my favorite. Yeah, so make a note that I primarily focus on the Steem blockchain, as this was prior to the recent, quote, cryptocurrency war between Steemit and Tron versus the Steem community, which resulted in a large portion of the Steem community jumping ship and creating the Hive blockchain, which is just a, quote, hard fork of Steem, which I'll discuss further in this series. and more so in part 2. So for a technical overview of blockchain technology, decentralized information, or decentralized information sharing, and the mathematics of cryptography, check out my blockchain overview video. That's this one here, or that's this in particular. So this blockchain overview video right there. So anyways, let's just jump right in. So introduction. So in this video series, I'll be looking at the quote big picture of blockchain technology, and by extension the overall direction and philosophy of mainstream technology in general. Technology, mathematics, science, and language are all tools. But tools for what? That's a good question. This is a guiding question that also serves as the answer to making sense of the past, present, and future technology. Blockchain technology, however, is a very unique tool, and one in which humanity has been pushed consciously and subconsciously towards since the dawn of life. So yes, very epic stuff here. Let's jump right in. So note on part 1. So I was planning on making just one video on the quote big picture of blockchain technology, but I felt the need to first fine-tune my own understanding of blockchain and present an overview of its fundamental purpose. This differs from my earlier quote blockchain overview video, which was focused on more technical aspects and specifically on the mathematics of cryptography. In this video, however, focus is on the driving force itself. So on the driving force of blockchain technology, and in particular, just what does it mean? Or better yet, what exactly it means to, quote, own something in digital form, such as the numbers on your bank account. Yeah, so let's look at this question right here. And this question is, what do you own? This is an easy question to answer, or is it? If you take something physical, like your phone, book, or any other object, you can, in fact, be, quote, satisfied by stating you, quote, own that object. Note that even this ownership is contingent upon the ability by which someone else can take it away, either legally or otherwise. For the purposes of illustrating the difference between physical and, quote, digital objects, I will define, quote, ownership as being physically in your possession. Yeah, something that you can pretty much hold or keep in your property. Then now that brings us up to the numbers on your bank account. So what about the digits on your bank account, which we call money? Do you, quote, own them? Can you physically hold these digital numbers? They can be viewed on your computer or smartphone, but they are not located there. So where are they? There are two ways by which you can claim to actually own these digital numbers, or at least practically. The first is if you go to your physical bank location and ask politely to the bank teller, showing your bank card and or government ID, of course, to withdraw the digital numbers into physical cash paper. And then the key, then hope they actually fulfill your request. Does your bank have enough cash on hand? Did you go beyond any arbitrary withdrawal or any arbitrary withdrawal limits? Did you read the fine print? Are you suspected of having dangerous independent thoughts on the internet? These are questions that you may have to comply with. The second way to claim ownership is to locate the exact computer that stores the digits of your bank account and ask if you can take that computer home, by which you'll be asked to, quote, be calm, be kind, and be safe until the police arrive. It is clear that the owner of the bank account is not us, and we can only hope the actual owners allow us to pretend like it is actually our money. So in other words, if you can't hold the digital numbers on your bank account, then you don't actually own the money. So your entire digital existence. Let's take our example of the numbers on your bank account and generalize it to everything digital. So your recent Facebook or Twitter or YouTube post got censored or deleted or stamped with a Snopes, quote, fact check, and you are upset. First of all, what gives you the right to be upset? How can you claim ownership that it was, quote, your post? Where is your post, or, quote, your post? Can you locate it? Can you physically grab it? And since you can't go to your local Facebook branch office and withdraw your post, then you have even less claim of ownership than the numbers on your bank account. Your social media profiles and all the data you have fed into them, along with your email accounts and your entire internet existence, is not yours and never was. So stop pretending otherwise. Thus your frustration as to how, quote, your social media post was treated by, in brackets, government subsidized tech giants is better aimed not at the censorship, but the fact that it can be censored. So that's the key point there. So now let's look at the internet, cables of light. So the internet can be viewed as the interconnected network of networks, which is essentially a bunch of computers, quote, communicating with each other. This communication is the literal transfer of light across cables, satellites, and electromagnetic transmission towers. And for the aether scientists out there, light is a vibration in the aether. Anyways, the transfer of light is in the form of, quote, wave packets or pulses, and the transmission is currently almost entirely transmitted mainly through many deep sea fiber optic cables. I think it's so almost entirely transmitted. You don't need the mainly there because it's already included in the sentence. Anyway, so through many, and caps lock, many deep sea fiber optic cables. And here's an illustration. This one's just water, actually. This is to show you how water, how light can bend inside or refract. And it just follows this path, and that's a laser beam shining to it. Just want to put an image. There's a total reflection in water, quote, bucket of light. Yeah, so this is from the Harvard Natural Science lecture demonstrations. A beam of laser light can be trapped inside a stream of water by suffering total internal reflection, the quadratic equivalent of a fiber optic cable. And here's the fiber optic cable, just to illustrate it, because so you have the fiber optic cables in here, so which is literally transmitting light. So you just shine a light, a laser beam, and it's sending that light across, and you have some protective layer, some copper, some insulators, and you got some steel wires protection, and you have this cover there, and this is deep sea, so we're gonna throw it all the way in the ocean. So yeah, here's just a physical one. This is a drawing, and this is a physical copy there. I have physical illustration. And now here is just an illustration of the installation of these wires in the ocean. So you got some big rigs there, some boats. And yes, just pretty epic engineering there. You got some machines here moving or placing it on the ground, pretty much clamping it down. Here is some seeing it physically on the shore. This is some highly bolted fiber optics inside. And then yeah, here's underwater. It looks like it's rusting and so on. It's fascinating stuff here. So I just wanted to include these images because this is a bunch of cables. This is the internet. So there's another big machine installing it and so on. And here looking at it, and there is many of these deep sea cables. It's from Submarine Cable Map, and there is many big ones all across the world connecting everywhere. And they're obviously going to have through the land as well. So this is the internet. I'll just write that down. The internet. Fascinating stuff here. Whoops. So yeah, just put it on there. So the internet like that, and I'll just delete it for just to make it a bit more clean and so on. But yeah, so that's the internet. Just a bunch of wires. So the internet is just the infrastructure and plumbing of light, just as a city water grid system is the infrastructure and plumbing of water. So for example, here's this water one here. This one's this is actually Vancouver, BC, Canada. So you got some rivers and aquifers and so on, and lakes, and then you got all this interconnected plumbing going straight to the city and so on. Here's just more plumbing in the house. There's the main drain and so on. You got the water lines coming in, electric, gas, and so on. And yeah, and here's under a city. You got the plumbing for sewage and stormwater and so on. So I just want to show that analogy with light. Alright, so now let's continue further. So World Wide Web, language of light. Although both light and water are transmitted primarily through cables and pipes, the ability to structure and pulse light at very fast speeds means it is a good medium for communications. The communication of light can be digitized, structured, and standardized in a specific set of protocols, mainly known as TCP/IP, HTTP, and the World Wide Web, or the WWW, which collectively form the basis for a uniform language that all computers and devices must follow to uniformly transmit and render information, such as the images on your screen or the audio of my beautiful voice. Thus, any computer can communicate to any other computer around the world so long as they have access to the Internet communications infrastructure and use the same uniform Internet language. Since the World Wide Web and the, quote, Internet are used synonymously, we can view the Internet as a language of light. And the Earth is a giant computer. So here's this is space station view of this is Europe, and this is nighttime with all the lights. Yeah, so yeah, this is all the lights, all the city and road lights, and so on. And it looks pretty pretty ridiculous. Like it looks like a circuit board, all lit up, and yeah, everything's connected with internet and electricity and so on. And now we continue further, and here's a good map of the world that has all the continents as a circuit board. So yes, computer. The world is a giant computer, and interestingly, interestingly, the World Wide Web was founded in 1989, and the first internet browser in 1990, and both of them at the European Organization of Nuclear Research, or CERN, the same folks smashing particles together with the Large Hadron Collider. So that's the founders of the World Wide Web, as well as the first internet browser. So yes, that's interesting. So the story goes, and here's from Wikipedia, that CERN computer scientist Tim Berners-Lee was frustrated with the lack of an efficient system to retrieve research and other information found in different computers, so he decided to develop the, quote, web, and he actually used that phrasing. So the internet itself, and here's again from Wikipedia, was developed by the USA Department of Defense as a means to share computational resources or time sharing of multiple computers in real time. And the first public, or in bracket public, communication between two computers via the internet, then called Advanced Research Projects Agency Network, or ARPANET, was on October 29th, 1969, just 3 months after the alleged moon landing on July 20th, 1969. In other words, while the world was focused on the alleged moon landing and multi-billion tax dollar particle smashers, the internet and the World Wide Web were being developed. Yeah, so while everyone's focusing on the moon landing and the CERN Large Hadron Collider and so on, or other particle accelerators, the internet and the World Wide Web were being developed and by the same governmental entities or similar entities. Yeah, in the case of the internet, was developed by the pretty much the military. So in summary, yes, the world is becoming a giant computer, and just as it was always designed to be. Hashtag buckle up, folks. So yes, it was designed for a purpose. And that purpose is it's to create a giant supercomputer. The entire Earth is a computer. So anyways, decentralization of information. The internet, defined as the infrastructure of interconnected computers transmitting wave packets of light mainly through fiber optic cables and using the same standardized protocol communication language, allows for information to be sent by anyone to anyone, and thus enabling the decentralization of information on a large scale. This transmission of information, however, involves sending duplicates or copies. Yes, that's the one issue. While the ramification of a digital printing press that can copy and paste entire books and transmit across the world in seconds is not to be understated, the issue arises when I want to send you just my exact digital book and not a copy. So if I want to send an email, for example, is there a way to send only the email, then it's gone. It's as if I'm sending a letter. In other words, I would like the ability to send a digital book in the exact same way I can give someone or sell someone a physical book. Better yet, how can I send someone cash digitally and without having to show my entire life's paper trail to my bank in hopes of them allowing me to transfer a few numbers on my bank account to another person with a different bank account, or without a bank account if they don't have one, and in a country listed as part of the U.S. empire's, quote, axis of evil? What if I just want to send someone cash that just happens to be in Middle East or something? So yes, these are very interesting questions. So let's go further. So decentralization of information, but not of value. So yeah, the internet allows for the decentralization of, quote, information, but not, quote, value. I can send anyone in the world, quote, information such as what the numbers on my bank account are, but I can't transfer those numbers across the world without first pleading to my bank. I can send anyone a digital copy of my book, but I can't ensure that they pay me for it without first, quote, pleading with giant corporations like Amazon to allow me, this is the key word, to allow me to post my ebook on their website and allow me to use their infrastructure of banking connections to facilitate the changing of digits of different bank accounts and hope that no one copies or sells my digital copy of my book. Remember, this is the current system that we're in. I can send anyone images of my house, but I can't sell them ownership of my house without first making a legal contract with my realtor, lawyer, and or bank, and only if the physical and legal infrastructure is in place between countries to do so, or in countries, or in states, or in provinces, and so on, or in cities, and so on. So there's got to be an infrastructure set up for that in this current scheme. So the issue goes back to our banking problem. I would like to send someone numbers from my bank account without a bank, or better yet, just more accurate, without going to a bank or asking them, or following their rules and so on. In other words, I would like to give people cash digitally in the same way I can physically. Yeah, so I would like to just give someone cash like this. Here's a bunch of cash. Give me your item. Here's cash. Is this a difficult question to ask? So I like to do this, but in digital form. Another question to ask is, what is value? So the question of, quote, transferring value requires first defining, quote, value. Quote, value is a subjective term and depends on who you are asking. But in practical terms, it is the dollar amount people price things at. As in Economics 101, we learned that the price depends on supply and demand. The higher the supply, the lower the demand, and the lower the supply, and the higher, the higher the demand. So basically, a simple supply and demand curve looks something like this. You have the price, you have the quantity, demand goes down like that with quantity, and then supply like this. Yeah, just a typical curve. And what this means is, if you're selling something like this, at this, you have this much quantity and you're selling at this price, the demand's going to push the price down. But it's going to push the price down, but you have a lot of supply, so you don't want to be making that much. But also, if you're selling something at this price right here, but the quantity is very low, it's going to push it up higher, but you're only selling a few things. So there's going to be an equilibrium point somewhere here. So basically, the curve would move it. Yes, you want to move the price here and the quantity here so that you're selling a sufficient amount at a decent price so that the overall sales is the highest, or the highest profit, as opposed to here, if you're selling a tiny bit at a high price, yeah, you may be only selling a few items, and you wouldn't have as much profit as if you were selling more. But then this is an equilibrium point. Let's draw this equilibrium. All right, enough Economics 101 for now. So, but regardless of the demand, if the supply is infinite, such as copying and pasting digital information, then the price or value tends towards zero. So demand for air is high, but supply is infinite. So you need it to breathe, but it's everywhere, so it's free for now. Thus, effectively, the first step to create digital value is to lower the supply. So air is free for now because it is abundant. Gold is expensive because it is rare, and then demand likewise, is an after effect of the supply. All right, now let's look at physical and mathematical one-way functions. So in the physical world, I can hand someone a book very easily, but if I were to duplicate it, I would have to either buy another one or type up the entire book and figure out how to print and bind it. It is easy to hand the book to someone, but it is difficult to duplicate it. So yes, I'd have to go to a library, get an exact other copy, or just go print it and bind it and make it somehow. But I can hand someone else easily, or sell it to them very easily, just hand it. So this can be viewed as a physical one-way function. Easy one-way, just hand someone a book, but hard to duplicate it. So let's go further. So one-way functions are possible in mathematics too. We can multiply prime numbers easily, but we can't easily determine the primes that make up the number. For example, 17 times 31 equals 527. So you can just put this automated one-note calculator. Like that, just automatically calculates 527. But going backwards is hard. So 527, to split it up into their two primes, 17 and 31, is hard. Note that prime numbers are just numbers that can only be divided cleanly by 1 and themselves. For example, 17, you can only divide it by 1. 17 divided by 1 is 17, and 17 divided by 17 is 1. You can't divide any other way. Same with 31. You can't divide it cleanly any other way. And then when we have a number such as 527, to find out what primes it's made up of, that is difficult. So now imagine the prime numbers are 100 plus digits long and require a supercomputer to compute. This crude example of a mathematical one-way function is the key to mimicking the physical one-way function of being able to hand someone our book easily, but having difficulty magically duplicating it. And this concept of functions that are easy to calculate one way but difficult in the opposite direction serves as the basis for all of cryptography, as well as serving to bridge the gap between digital and physical objects. So let's look at physical boxes and cryptographic hash functions. So if we place our book inside a box, then close it up and tape it, how would anyone else know what was inside the box? So let's put our book inside there. For others to find out what was inside the box, they would have to physically open it or to get an x-ray machine and scan inside. Either way, it is not easy. To drive the point further, since boxes are easy to open, let's instead put our book inside a metal safe box and then forget the password or throw away the key so that even we can't open it. So put it inside the safe box. So yes, if we put our book inside the safe box, forget the password, throw away the key or whatever, however ways it is to open it, and then basically no one's going to get inside this box. It's a pretty strong safe box. So yes, no one will open this box. This is just another type of a physical one-way function. We can easily place any arbitrary object inside the box, but for others to find out what is inside the box, they would physically have to open it to know what is inside. The mathematical equivalent is called a, quote, cryptographic hash function, in which I went over in my blockchain overview video. So here's a link to that earlier video. And this was from Wikipedia, the cryptographic hash function. So the input here, let's say you have a text like this, Fox, and then you throw this inside this one-way mathematical function, a cryptographic hash function, and then what it gets is a string of characters, string of letters and numbers. Yeah, and it's called the digest. So you throw this inside, you get this. This is pretty much like a safe box now. And this is a mathematical one-way function that it is easy to throw this just any input, like for example Fox, inside this function to get a random digest like this. But it is very, very hard to go from this. It's very hard to go this way all the way to this to see what's inside. So it's equivalent to our physical safe box. So that is equivalent to this. So that is this right there. And likewise, if you just add something here, for example, if you add something else, we'll have another seemingly random string of digits like that. So the red fox jumps over the blue dog. And if you just change one character for this, for example, over, change it to a U, it's completely different. So that's the key to making a safe box, a digital safe box, or cryptographic hash function. So hash functions involve mathematical algorithms to convert arbitrary information into a standardized string of information. To convert data into a, quote, hash or, quote, digest is easy, but to go in the reverse direction is very difficult. Thus, effectively, we have placed our digital box our digital book inside a digital box. So that's equivalently, that's what we have done pretty effectively. Although in the digital world we can still copy and paste a digital box or hash, but like the physical world, we still can't easily see what is inside our box. So yes, that's the key difference. Is we can put inside a digital box like this, but we can copy and paste it infinitely times. We can copy and paste this string of digits and send it to everyone, but they still can't just go and find out what's inside. They'll just have a second copy of this, and a second copy of just a string of digits. It's not having anything. Yeah, so in other words, what good is copying and pasting a random string of data if we can't read our book? So yes, let's get a random string of digits. So digital keys, passwords, and cryptography. So in our safe box example, I purposely, quote, forgot the password or, quote, threw away the key. But instead, or if instead we keep the password / key, we can now open our safe box to see our book inside. And mathematically, we could do the same with our one-way hash function by ensuring that the function has a, quote, secret key to, quote, encrypt and, quote, decrypt our digital book in our digital safe box. So again, this is from my blockchain overview video. So if you had a secret key like this that you can encrypt, so you could put inside the box, and decrypt to open the box, it's equivalent to having just a key to our safe box. This basic lock and key form of encryption or mathematical digital safe boxing is known as symmetric key cryptography, since both the sender and receiver share the same key. So in other words, if we have Bob here and Alice, they both have to use the same key to open the box and decrypt the box or unlock the box and so on, or this cryptographic hash function. Yeah, so symmetric key cryptography is just like a physical key. So the term cryptography, or the term, quote, cryptography, refers to the entire discussion we were having. So the entire discussion we are having now, and it is just the science of sending private or cryptic messages, or as per my own practical definition, MES definition, cryptography is the exploration of one-way functions. Yep, that's how I view it. So a major issue that arises with this form of lock and key encryption is that the more digital locks we have, the more digital keys are required, and managing 1 million keys is no easy task. Yeah, while using one key for 1 million locks raises a quote few safety concerns. So yes, if you have 1 million boxes all with different keys, it's gonna be hard to manage all those keys. But if you have 1 million boxes with one key, then you gotta worry about losing that key, and then you lose all your boxes, or someone steals it, and now all your boxes are gone. So the other major issue is that the secret key needs to somehow be shared amongst the sender and receiver privately as well. And again, we're in the digital world, so if we have this encrypted but the key's not, and how are we going to send that key then? So that's another issue. So symmetric key cryptography was the only publicly known form of encryption until June 1976, when Whitfield Diffie and Martin Hellman, interesting, totally non-secret society occult last name, Hellman, signaling trickle-down technology, #sarcasm. Anyways, ignore that, please. Published a paper on, quote, public key or, quote, asymmetric key cryptography. And again, for my blockchain overview video, so what do we have here? So if you have if Alice creates two keys using a large random number generator, and you get a key generation program that creates two keys, public and private, that are mathematically linked. The private key can verify the public key, but the public key right here, the private key can verify and create a public key, but the public key can't easily create a private key. So the one-way function goes from the private key to the other side, like that. And the asymmetric key cryptography, or the public key cryptography, looks something like this. So if we have Bob is over here, and Bob writes "Hello Alice," and then encrypts it. He can encrypt it with Alice's public key, because this can be public. Anyone can know what it is. It's like an address. And then so he encrypts it like that, and then the only person that can decrypt this box or open this box is Alice's private key. So now Alice. So this person, everyone has access to the public key, but only Alice can open it, and this one you're supposed to keep it private. So you can decrypt that like that. And likewise, other schemes can include like this. So you can have Alice right here can take Alice's private key and Bob's public key, and then can combine the keys together, and then create a safe box that has Alice and Bob's shared secret key, and then Bob can open open this box by using Alice's public key and private key. So there's different ways of doing the same thing here. So the private key is the one that's hidden. Public key is public. So yeah, you could either combine or you could do it like this. But yeah, so there's different schemes of the same idea. So this form of cryptography involves a second one-way function, this time using our private or secret key to mathematically generate a secondary public key. Thus, we can use our private key to easily generate a public key, but it is difficult going the other way to generate a private key from a public key. The public key, which anyone can publicly see, because remember, it's a one-way function, it's hard to get the private key from it, can now be used in our newly upgraded one-way hash function to encrypt any message. And in general, this means that anyone can encrypt any message using our public key, but the decryption can only be done with our private key. The physical equivalent of this new digital public-private key scheme is akin to our house public address and a private house key. Anyone can look up and deliver a box to a home address, but only the homeowner can bring it inside using the house key. So yes, this is the public key. Right here's the address. That's public, so you can deliver a box there, and then only this person can open it up, or open this box. Only this homeowner can bring this box inside. So you can deliver any message to it. Only this person can open the door and go inside. So that's the private key. The private key is to open this door. The public key is the address where the door is located. Yeah, so now let's look further at let's look at digital signatures. So if the mail person delivers mail to our home address, he or she or they may require a physical signature. So yeah, so there's the mail person or the mailman delivering boxes, and then if they require a signature, you can sign it, and then they'll know that this person signed it. So the concept of signatures is another example of a one-way function in that it is easy to sign something, but it is difficult in theory, because you can always fake it. it is difficult for others to replicate our signature. Yes, again, in theory. Converting physical signatures to a digital equivalent can also be done using public key cryptography, this time using the private key to sign, while anyone can publicly verify using the corresponding public key. So for example, here, if Alice right here puts, there's a hello Bob message right there, and then they could sign this message using the private key, so that this message has a cryptographic linked hash that, or just a box, or just a signature that states that Alice has signed this message. Now Bob can verify this message was signed by Alice's private key by just using Alice's public key, which is public. Just verify. So anyone could just go verify that this signature is actually this private key. This example shows that even if the message is not encrypted or secured, the digital signature gets stamped onto the specific message, and any changes to the message will remove the signature. Thus, we can verify whether the message has been modified or not since the time it was signed. Remember, even if this message is not secure, but the signature is. So this means that Alice has looked at this message, whether it's secure or not, and has signed it. And that signature, or that signature verifies that the person Alice has actually looked at, or whoever has a private key has looked at that message, whether the message is secure or not. It just means that the signature is secure. So it's fascinating stuff. Alright, so now that we have private and public keys, gone over private and public keys, we're more equipped to now look at the numbers on our bank account again. So thus far we have shown that mathematics and computing allows for the mimicking of physical objects such as books, boxes, houses, and signatures, but what about the numbers on our bank account that started this entire discussion? How do I change those without begging my bank? The answer is simple. You can't, because your bank has both the private key and the public key, and you have nothing. The only person that can change numbers on the screen is the one that they physically belong to. Thus, the bank, quote, the bank owns, quote, your money, and merely allows you to have the illusion of ownership so that you deposit more of your cash to them. To claim ownership of the numbers on your computer screen, although not on your bank account, we can follow the steps thus far covered. So we can generate a random private key, mathematically generate a public key using our private key, and then print the private key and hide it under our bed, or under my bed. Type $1 million into a message box. Into a message box anywhere outside your computer. Mathematically generate a hash of our message using our public key, and then mathematically sign the hash using our private key. And these last two steps are pretty much interchangeable. One has a signature, the other one you can just use the public key, and it can only be opened by the private key. So on. So regardless, so congratulations, we are now millionaires. We can rightfully claim to, quote, own a piece of digital text that says $1 million, secured by a unique private key that no one can access but us. There's only one tiny little issue. No one will accept our million, quote, dollars, because they don't have to. Physically, all we did was write the number 1 million onto a piece of paper and hid it under our bed. We can claim ownership of the paper that the number is written on, and that's it. Now the question to ask is, whose ledger is it anyway? So far, what we have done is effectively created a ledger with the first entry as being a money printing of $1 million to ourselves by ourselves. We are now our own central bank. A, quote, ledger is just a record of events, while the term refers mainly to financial transactions. You have opening balance, just money in, money out, etc. So just a history of events is a simple illustration there. So our ledger so far looks something like this. MES cash money, $1 million, and we hid it under our bed. So yes, we have this paper. We have a ledger, and it's a network of one person. So our bank's ledger looks something like this. If you go to a bank, they usually have something like this. You've got a bunch of accounts, bunch of different properties, and so on, a bunch of balances and numbers, and so on. So the USA's government ledger looks something like this. This is retrieved October 23rd. There's about $26 trillion in debt. So that's what their ledger looks like. Just debt everywhere. And the world's ledger looks something like this. So here's USA, China, and so on. You got 26 trillion debt. China's 7 trillion debt. This one's 12 trillion debt, etc. And this is all just printed. It's all just printed money. So anyways, continue further. So now the question asks, where are the ledgers located? So to change the numbers in each ledger, we would have to go to, quote, where the ledger is stored and update it. Our digital safe box ledger is stored on our computer, and we can change numbers using our private key to open up our digital safe box and then digitally type digitally update our digital paper ledger. So we can go inside the box, see what the numbers are, and update it, and then lock it again. So our ledger looks something like this: MES cash money, $1 million plus 100,000, and now we just printed another 100,000. Yeah, so we have $1,100,000 of paper MES cash money. So that's what we have in our ledger. So our bank's ledger is also located in computers, but not our computers. And we can represent this by the physical bank location. So if you want to go to the bank's ledger, it looks something like this. We're probably in a server somewhere else. But just for our purposes, it looks something like that. The USA ledger can be represented as being at the Federal Reserve. So you want to go to their ledger, you got to go here and update it. And the upcoming World Central Ledger will likely be constructed as per the biblical Tower of Babel. And this would be the world's ledger. So yes, the great work, the quote, great work is upon us. So that's going to be the world ledger. So yes, it's going all the way up to this, guys. It's a pyramid too, apparently. So anyways, value is in the collective belief of a network. So our digital piece of paper with quote or with $1,100,000 is worth $1,100,000 to us, or more specifically to me, since only I have possession of it and only I have pledged allegiance to this almighty MES dollar. To me, it is worth $1,100,000, but that is all. I'm a quote network of one. So there's me, myself, and I. All right, continue further. So compare this with the quote fiat money network, which typically involves central banks printing money and lending to commercial banks at interest, by which commercial banks lend to the public at higher interest. MES note, quote fiat simply means an arbitrary degree, and quote interest is simply the cost of money itself. So they print money, give it to someone, but then they have to pay back a percentage each month or each year and so on. And the system looks something like this. So you have a central bank prints money and then charges, let's say, 2.25 interest. And then the banks have to find a way to pay that back monthly or so on. And then the commercial banks loan the money out to people for houses and so on at higher interest, like 3%. And then these people have to work and somehow get that money and throw it back. So it's a giant scheme, but all of life is a giant scheme, a giant Ponzi scheme. Anyway, so fiat networks have mainly people entrusting their hard-earned cash in the collective belief that others will accept it in exchange for goods and services. So 1,100,000 USD is worth a house to millions of people, but 1,100,000 MES dollars is worth a house to one person. So yes, it's the collective belief. So if you have $1 million USD, a lot of people will accept that, and they'll be able to get that house. But if you have $1 million or $1,100,000 of MES dollars that we just printed out of nowhere, only I accept it. So yes, it depends on the collective belief. Collective belief of one person versus collective belief of millions. Now let's look at the concept of trust. So even if a network of people believe in the value that numbers on the bank account represent, they still have to place their trust that the banks, governments, and other institutions of people are accurately maintaining a ledger of all the transactions within the network. If I buy a house for $1,100,000, then my bank balance should subtract it from the current numbers on the bank account. Now let's assume that I can somehow persuade or mind control others to join my network, as well as convince them that $1,100,000 MES dollars is worth their house, and now we just need to update the ledger accordingly. All right, so let's look at our ledger again. So we have MES cash money. We had the 1 million. We printed 1 million. We printed another 100,000, and now let's buy a house. So we're gonna minus from this balance. So we're gonna minus 1,100,000. So we have zero balance, and then the house seller, whoever sold us the house, has plus $1,100,000. So that's what we have the ledger, and we've convinced someone to believe in our piece of paper. So we are now effectively a bank and have full ownership of our digital paper money, but just one problem here. The person that bought our house from now has the same issue which we started off. They have to trust that we accurately maintain the ledger and trust that we will change numbers on their bank account upon request. So all we've done is now we've become the bank, but now the seller's wondering why am I trading my house with this piece of paper? Yeah, so instead of that, let's give the copy to him. So if instead of maintaining just one ledger, we could give a copy to the other member of our banking network. So here's MES ledger copy, and here's the house ledger copy. So we have both copies. So now we can both see that we both have it, have a copy of the ledger. So for both banks. Now the issue is we need to ensure that we have the exact same ledger for all new transactions and that neither one of us tamper with the ledger. So let's look at a chain of signatures. So to ensure that the ledgers are not tampered with, we could ensure that each transaction is signed off by each person sending money. Yeah, so physically this would involve both accounts to sign, copy, and send the ledger to each other to ensure both are in agreement as to the latest up-to-date ledger. So here's the MES cash money. So we just sign the money printing here, 1,100,000, and then we sign the subtraction that we're buying this house, and then we send it to the house seller. Just copy and send, and then they sign off that okay, they are okay with the money that they received, and we just give them the house. And now, yeah, they would copy and send it all the way to MES. So now the house seller and I have the exact same, and they're both signed. So we know that they both have signed off on that. So now copy and paste and double spend. The issue that arises in decentralized systems is that information can easily be copied and pasted, which raises an issue known as, quote, double spending, which is effectively counterfeiting money. This is an issue that arises more frequently as the size of the network increases. So if we add another person to our network, and instead of just buying a house, we can copy and paste our ledger and then purchase both the house and the car with the same money. Or a car. Let's say buy the house and a car. So here's MES cash money. So instead, let's go back to our money printing. So if we have something that looks like this, MES, yeah, so MES just made it bigger. So MES cash money, so $1 million printed, we signed, 100,000 printed, we signed. So we signed that off. And then we copy and paste, but you can do that digitally, you can do that easily. So just copy and paste, send it to this car seller and the house seller over here, or actually before we send it to them. So we just copy and paste and then add a car purchase of $100,000. So the balance is 1 million. And then we would add 100,000 to the car seller, person selling us the car. Likewise, it's the exact same with the house seller. So we subtract $1,100,000, and then add in the ledger that the house seller gets $1,100,000, and then send this copy over to the house seller. But then at the same time, we're sending to the car seller because we just copy and paste this, add the little notes, and now the house seller or the car seller signs off saying they got the money, they got the ledger, and the house seller, the car seller does it in the house sellers. But now we have two chains. So we have from the one ledger right here, and then updating it, we just copy and paste, and we get two different chains, hashtag two chains. We've effectively spent the money twice, or double spent it, and are now left with two ledgers. So in other words, we had this money that we could buy a house and a car, which is not a ledger. But a ledger is a record of transactions and not two records. If you have two ledgers, you have none. So in other words, if this house seller finds out they're double printing, or this car seller finds out this guy's just printing money and buying it, they'll realize he's either the government or let's go to a different bank or a different network. Or to call the police because you're getting scammed. Anyway, so chain of digital signatures. Digitally, this is the same as a chain of cryptographic signatures. In fact, that is all a ledger is. A digital ledger is a chain of digital signatures. The Bitcoin, quote, white paper illustrates the use of transactions signed with private keys, verified with public keys, and linked with hashes, our magical digital one-way functions. Note that, quote, white paper is an informational document describing the general design and purpose of a concept or product and used for promotional purposes and not a technical manual. Here again from my blockchain overview video. Here's from the Bitcoin white paper at bitcoin.org. Yeah, this is a pretty good write-up from the Bitcoin white paper. So we define an electronic coin as a chain of digital signatures. Again, that's pretty much all a digital ledger is. Each owner transfers the coin to the next by digitally signing a hash of the previous transaction and the public key of the next owner and adding these to the end of the coin. A payee can verify the signatures to verify the chain of ownership. And so basically if we have something like this, let's start from owner 2 right here, or owner 1 right here. We take this entire transaction, remember, throw this in our magical hash function, which is just our digital box that we put stuff inside. So we'll put the previous transaction, let's put this entire transaction into this, plus the owner 2's public key like that. So we create a uniform box or hash, and then that's signed by the owner 1's private key. So the private key is signed this one, so we have a signature that can be verified using the public key. And then we keep doing that for the next one, and so on So we have a chain of these signatures, and a payee can verify the signatures. You just check each person's public key and check if it's verified. So we'll check that says yes, it was signed by owner 2's private key, and so on. And then the problem, of course, is the payee can't verify that one of the owners did not double spend the coin. So how do you know if these ones didn't copy and paste and just double spend elsewhere? So that is the issue. A common solution is to introduce a trusted central authority, or mint, that checks every transaction for double spending. In other words, become a bank. After each transaction, the coin must be returned to the mint to issue a new coin. So just like with a bank, you got to always go to your bank and do a transaction, go to bank, do a transaction, and so on. And only coins issued directly from the mint are trusted not to be double spent. The problem with the solution is that the fate of the entire money system depends on the company or bank running the mint, with every transaction having to go through them, just like a bank. So yes, that is the issue we don't want to deal with. We need a way for the payee to know that the previous owners did not sign any earlier transactions. Yeah, so for our purposes, the earliest transaction is the one that counts. Yeah, just get the earliest one and deal with it. And then, yeah, hopefully that chain matches other people's chain, and so on. Yeah, so we don't care about later attempts to double spend as long as we can get a consensus from the earliest chain that matches other people. So the only way to confirm the absence of a transaction is to be aware of all the transactions. Yeah, so if we're aware of all the transactions, yeah, we can find out if something's missing or not. So in the mint-based model, the mint was aware of all transactions and decided which arrived first. To accomplish this without a trusted party, transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they were received. So that's the idea. Just agreement. There needs to be an agreement. The payee needs proof that at the time of each transaction, the majority of nodes agreed it was the first received. So our double spent chain of chain of digital signatures. Chain of digital signatures. It looks something like this. So here I have it in blockchain format. So here is our MES account name, MES print money. So that was a transaction, and then 100,000. MES balance is 1,100,000, and this is there's a previous one there. So we have a transaction hash that includes the public key, and then we create MES signature like that. That can be verified using the private key, the previous one there. Anyways, let's continue further. So then now here we sign two transactions, or we copy and paste and just sign two transactions. So here's the double spent one here. So transfer to the house seller. We transfer amount 1,100,000. MES balance 0, and then house seller's balance is 1,100,000. And then we combine the house seller's public key, which is just public, anyone can see it, just public address. And then we combine this, so this entire hash, combine this into the transaction hash with the public key. And it creates a digital signature that is signed by the private key right here. So this signs it over here. But we do the same thing over here. Let's make this maybe a bit bigger. But we do the same thing with the car seller. So just copy and paste. So with the car seller, transfer amount 100,000, MES balance 1 million, and then we have over here car seller's balance 100,000. And we combine the car seller public key with this hash right there. Combine this into that, and then we can sign off. The private key signs off on the MES signature and here. So now we have two chains. Yeah. So this is just a blockchain version of it, or the Bitcoin blockchain version of our ledger, or double spent ledger. So we gotta find a way to have everyone agree on one chain of events, and then null the other side, or make it invalid, the other one. So consensus is everything. Double spending means our ledger can always branch out into multiple ledgers, but we don't need one ledger. We just need, quote, consensus of enough people to only consider one ledger valid. We could have 1 million ledgers. But just as you can have 1 million monopoly paper money, but as long as enough people value one of the paper money, such as the USD, as actually valid to buy the house and so on. So it doesn't matter how many ledgers you have; it just needs to be consensus of how many people value it. So a common way is to view only the longest chain to be valid. And then only build upon that as well. So here it is from the blockchain overview video. That's from Wikipedia blockchain. So here is a chain of blocks. There is blockchain formation. The main chain, black, right here, consists of the longest series of blocks from the Genesis block, green, it's the original one, the first one, and then to the current block right there. Orphan blocks, purple, exist outside of the main chain. So there's a double spent But it doesn't matter if there's double spend, as long as everyone agrees that we're just going to go with this right here. So that's the agreement. Or if other people agree with this one, you could split off and have other people go and deal with that one. But it's never consensus, or the value of the network is just a collective belief. You can have multiple different beliefs of what's valuable. But yes, so the idea of Bitcoin blockchain is to only build on the longest one. So in this scenario, the quote side chains have the possibility of overtaking the longest chain, which thus compromises the entire ledger, because it would mean the reversal of transactions. So yeah, if people were following this blockchain or trusting them to hold their value, but now all of a sudden there's two different spending, then now they have to choose which one is valid for them and which one is not. So it's an issue of managing consensus, so that if all of a sudden there's a double spend and then your house purchase was considered invalid, and then consensus switches to a different chain, all of a sudden you have just a bunch of worthless $1 million paper money or digital paper money that nobody trusts or nobody is valuing it. So yes, when you have side chains, and then if they have the possibility of overtaking the longest chain, all of a sudden people are using the new chain instead of the old one. This compromises the entire ledger, because it would mean the reversal of transactions. So, for example, if someone sent you $1,000, imagine if it was reversed a week later when the side chain becomes the main chain. So, in other words, they send you $1,000, but now all of a sudden you've been planning your entire day and life on that, and all of a sudden it's gone. So. Compromises, yeah, that's how you spell it. Anyways, going further. So effectively, we need to incentivize the network to add to the longest chain, and only the longest chain, so that the side chains become increasingly further behind. Note that the nature of the internet is such that the information has varying sending and arrival times, so new side chains may occur unintentionally. So for example, you have a computer here, a computer there, you're trying to connect to it. They could follow a different pipe or different light. Pipe of light, or a different deep sea cable, and or Wi-Fi or satellite and so on, and it can get to it at a different time. So it could happen unintentionally in the internet. So so it could be done intentionally or unintentionally to create side chains and double spending and so on. But even if new side chains occur, the network of computers upkeeping our ledger can temporarily maintain the new side chains until one is longer and then switch over. This is why many blocks suggest users to wait until multiple blocks are confirmed before designating their transactions as quote confirmed, which indicates that it is mathematically unlikely to get reversed. So for example, in this case right here, so if there's a double spend right here, or this or this is after one block, so basically most blockchains will say just wait for more confirmation. So wait for another block, so it goes right here. So if yours was inside this one, goes into another one, all of a sudden there's a split right here. Yeah, it would still say just wait for, let's say, 5 or 6 transactions, or 5 or 6. Let's see, this is 1, 2, 3, 4, 5, 6. Let's say it's 7 right here. So wait for 7 blocks to confirm, and then if your transaction went from here, so this is the one, and it goes through all the way across here. So you could be rest assured that it is confirmed, even if there's breaking up into side chains, because these would be included in every single one. This would be included in this one right here, and this and this. So they're all still inside it. So that's the idea of just waiting for multiple confirmations, so that mathematically it would be very hard for this transaction to overtake that one. But this one could be easier to overtake. So yes, that's the idea of it. Alright, so now let's continue going further. So digital gold, consensus via mathematical work. The Bitcoin white paper was the first publicly shown method of overcoming the double spending problem, and thus be able to create a stable consensus. And thus was able to create a quote stable consensus where mathematically it's going to be agreed upon the longest chain, and it's very hard to change it. The general method is summarized below. Batching up multiple transactions into a block, this is for Bitcoin one, and then maintain the hash of the hashes of the transactions, hashtag hashception. This is called a hash tree or Merkle tree. Timestamp the creation time of the block, chain to the hash of the previous block, and then increment an arbitrary number called a quote nonce until the hash of the current block, including the nonce, is below a specific target hash value. The successful block producer is rewarded with Bitcoin. So in other words, the blocks looks something like this. So data structure of the blocks in the ledgers from the Wikipedia, and also this from the Bitcoin white paper, but just it's a bit better diagram than the Bitcoin white paper. Yeah, so you get basically a bunch of transactions, put in a hash, and then you get that hash of different transactions, combine that into one hash, and then combine that all into a root function, right, or root hash. So basically putting boxes into boxes into boxes into boxes to get one uniform box that contains everything. And then get a timestamp, and then you have a previous hash all the way inside there. And then this is just a random number, so you keep incrementing it by 1. So you increment it by 1, and then trying to get this into this hash that matches a specific criteria, such as until the hash of a current block, including the nonce, below a specific target hash value, or has string of digits below or above. Below a specific size. So you're gonna have to do a million times, a trillion times with a supercomputer. And then all of a sudden, once that is approved, you can finally include that into a new block. Effectively, all it does is just slows the block production time. Yeah, and I'll just write that down. So essentially, this just slows, put that block bold, slows a block production time so that there will be enough time for consensus to be reached. Yeah, so if they didn't have this this mechanism of proof by work, this is just getting didn't have this increment arbitrary number and then solving this random hash function. Then you can have many different double spends because you can have an infinite amount of blocks being produced at super fast, and then create infinite different kinds of history. So you're going to have an issue with that because the network of computers doesn't have enough time to reach consensus. So that's why the idea is to slow it down so the blocks are going to be very few relative to the amount of transactions and computers in the network, and then so they can block it slowly. So now you'll have a way of being able to catch up to this rate, and then all of a sudden you can all choose that, okay, this is all one block here. So for example, if this takes 10 minutes to solve right here, this next block, it's much easier and much less likely to get a double spend than having 1 million of these blocks all added per second. So yes, that is the interesting part. So this effectively involves mathematically solving a hash or a one-way function. Recall our example of finding primes. So you have 17 times 31 is equal to 527. By going backwards, 527 equals 17 times 31 is hard. So yes, it's basically the idea is to find these numbers. That's the idea. This process means one thing: we can't just copy and paste our ledger and then double spend, or copy and paste our ledger as before, and then double spend for the house and car. We have to work for the money. So we have to put in the resources to actually go through this arbitrary nonce. This mathematical work calculation and to find these random prime numbers, for example, in our simplified one-way function example. So we have to work for the money. This is akin to going into a mine and start digging into the ground to find gold. We now have ourselves digital gold. So this is the only way we can get this $1 million. We have to go and dig into the digital mine. So this is what we have so far. So MES account, $1 million, and this is a bar of gold. So if we wanted to keep our $1 million gold bar and quote double spend it instead, so if we don't want to use that, we want to double spend instead, we would have to do this to the ground unless you can figure out suppressed alchemy science. So yes, that's for another day. So this is what we have to do to the ground to double spend. We'd have to go and dig into the earth and dig into the earth to find our gold bar, or to find enough gold to make that bar. So we have to do a lot of work. But to do mathematical work, we need mathematical tools, we need computers. In a, quote, proof of work consensus model, consensus is, quote, voted upon through computational power. And when the incentive is to be rewarded for digital blocks of digital Bitcoin gold, then the new gold rush is located at massive digital mining facilities. So here's Bitmain. Here's a massive one. This is in China. Why the biggest Bitcoin mines are in China. I believe USA is catching up as well. So there's a bunch of computers. All they're doing is just incrementing those little nonce numbers until they solve a hash function. All they're trying to do is open up a digital safe box to get a reward, which is a Bitcoin, digital gold reward. So these are a lot of computational power. Anyways, going further, this means that in our ledger for 3 people now, we can't simply add new transactions as we wish, but rather we have to compete with the network in digging through a digital mathematical mine in hopes of earning a profit in the form of new printed, created, mined MESD tokens. And also, I was contemplating adding this here, but yes, for the next step right here, and then gradually make it or gradually increase, or actually periodically. I put it here. So periodically increase the mining difficulty to catch up or to account for increasing technology. Or just write that better. So periodically increase the mining difficulty to account for future advances in technology and or mathematics. So if you find a better way, you have to update that as well. Or if you got some quantum mechanic mumbo jumbo as well, you're gonna have to update that difficulty as well. So yeah, so now we've added a system where you have to work to add new blocks. So digital governments, consensus via network stake. The consensus mechanism of mathematical work employed by the Bitcoin blockchain has spawned several approaches. Well, several different approaches, or just different approaches to consensus. A common consensus method is called, quote, proof of stake. While proof of stake involves competing with the network to compute the next block, proof of stake, however, shifts the block production process towards specific, quote, validators based on their stake in the network, and that is the amount of tokens they have. So in general, proof of stake, or POS, consensus schemes involves randomly selecting validators and their, quote, validation capacity based on the amount of tokens they have, and then rewarding validators for each transaction block they, quote, validate. And I'll just put it right here. So rewarding through network, or just through fees. Yeah, for each transaction block they validate. And the fees could be from whoever's making a transaction, or just printing money from the actual network itself, and so on. So just inflation or other ways. So the main difference between proof of work and proof of stake is that the commodity that is incentivized is computational power in the proof of work system, or POW, and obtainment of tokens in POS. And here's just a simplified comparison right here. So proof of work versus proof of stake. For mining capacity depends on computational power, and validating capacity, and there's a digital safe box, validating capacity depends on the stake in the network. So the more you have, the more you can validate. And then this one here, more computation, the more you can dig up the for the blocks. And then miners receive block rewards to solve a cryptographic puzzle. If validators do not receive a block reward, instead they collect transaction fees as a reward. And then for the proof of work, hackers would need to have a computational power more powerful than computational powerful than, or a computer or a computational power more powerful than 51% of the network to add a malicious block, leading to a 51% attack. So if you can form consensus with a bunch of computers trying to attack the network, and then that's the way to attack it. So you just need to get all that computational power. Otherwise, for the proof of stake, hacker would need to own 51% of all the cryptocurrency on the network, which is practically impossible, and therefore making 51% attacks impossible. So yes, it would have to go and buy up all of the tokens. But if you're buying up all the tokens, the price is going to keep going higher and higher, unless people are going to start selling to you. So in other words, you need infinite money. Yeah, this one you'll need infinite computational power. This one you'll need infinite money to attack this network. And going further, so variations in digital governance. While proof of work and proof of stake were amongst the first consensus mechanisms achieved, even more variations have branched out, and some that don't even utilize the blockchain. One variation is called, quote, delegated proof of stake, in which stakeholders vote on the validators or, quote, witnesses, and can upvote any bad actors. Yeah, so you can include a voting mechanism with the stake, so you can vote with your how much tokens you have for these validators, and you can unvote any bad actors. So then, so you're incentivized to follow the rules, or else you get voted out. And the Hive and Steam blockchains utilize this DPoS, or delegated proof of stake, for consensus. Ripple's XRP cryptocurrency uses an quote, iterative consensus process in which a node receives and sends transactions to the rest of the network while maintaining a specific list of trusted nodes called unique node list, or UNL, to check each transaction with. Each iteration is batched together and given an, quote, approval percentage rating based on how many times it matches the UNL. When the approval rating reaches an 80% threshold, then the ledger is, quote, closed and deemed to reach consensus. A new ledger is started, and all previous discarded transactions have a chance to get approved in the new ledger. So here's just this is the video that illustrates it pretty decently right here. So you're going to have a specific list of computers or people that you trust, and then you would compare whatever transactions come into here and give it a rating or a vote to see how much it matches up with these ones. And once it gets to a certain specific number of approvals, then you could just say, okay, this is good enough, and you would sign. So to say that more than 80% of this have that exact same transactions. Sign it off, send it over, and then all the ones that aren't part of it gets discarded for future. Yes, they get discarded for the future, and then hopefully try to get to for a new ledger once it's open. So once this one closes, say this is all consensus, and then you start off with a new one as well. Remember, the idea is just to get consensus. That is one of the key, and the security and so on depends on how you're doing it and what is the ultimate goal. So that's with the XRP ledger. There is only one ledger at all times. There is no blocks or chains. Instead of a chain of blocks, and thus no side chains either. So you also have just one ledger. You throw transactions in, and there's a trusted group that you have. And then when the entire network has a specific 80% threshold, it will consider it all valid and go on. Yeah, so another new consensus mechanism is utilized in the Hedera hashgraph cryptocurrency, which differs from the basic blockchain mechanism of maintaining only the longest chain of blocks, but instead incorporates the entire transaction history and, quote, weaving it together. So let's put this add to dictionary. So this is the typical blockchain one, or how Bitcoin is. So you're trying to maintain the longest one, and you would basically cut off all the other side chains. Anytime there's a double spend, you would just cut this off, and just maintain with this vertical one right here. But you would need to slow it down with proof of work. Hashgraph instead just combines every single one together. So it takes all this and then weaves it all together. So that even if there's some double spending, as long as the overall history is going to eventually reach one specific area, as opposed to spreading all around, as long as there's one general consensus. Yeah, so it doesn't matter if there's one uniform version of events, as long as there's a consensus of what happened. Even if you go, there's an invalid one, or there's a double spend, there's a duplicate. As long as everyone agrees that there's a duplicate, you can work around it. So there's different scenarios have will have this kind of possibility. So such a mechanism focuses on speed rather than complete linearity in the transaction, and has suitable applications in live streaming videos or in video games, in which a split-second duplicate or double spend of an image that the human eye may not even detect is worth the resulting increased consensus speed, without needing a proof of work mechanism to slow down the blockchain. So yes, in other words, even if if you're watching a movie and there's all of a sudden there's like a half a second of duplicates or double spend, and it goes back there, as long as the entire overall image of the video is decent, that's good enough. So this one has different target audience or target or user end than for example the Bitcoin blockchain, which is everything needs to be exactly perfectly linear and then slow production, like for example like physical gold or digital gold. This be gold. This could be like videos. Yeah, let's put that here: video or video streaming, or just any kind of just a video or any kind of live streaming or so on. Or even micropayments of banking or so on, or whatever scenario that may be needed. But again, that is up for the users to decide, and the overall security and just how it works for you. These are but a few concepts in the science of reaching consensus. So anyway, so decentralized, this can be like a mini summary. Decentralized consensus everywhere and nowhere. So the main discussion in this video was in regards to the concept of, quote, ownership, and in particular the numbers on your bank account. Physically, we can be satisfied with our claim of ownership when we can hold a physical object in our hands, such as the fiat government printed paper money. But digitally, the numbers on our bank are just bits of information, which are just tiny duplicated pulses of light in our internet plumbing network. Information is just the abstractions of communication, the abstractions of a language. That's all this quote information is. Thus, the question of physically holding information has no fundamental meaning in of itself. Rather, information only has value, only has meaning or, quote, value when others agree that the numbers on my bank account have value. Information only has value when it has, quote, consensus. In a centralized consensus scheme, the value of the information has the additional burden of trust in the central authority managing the numbers on your bank account. And yeah, but our use of the mathematical one-way functions, or our use of mathematical one-way functions used to develop private keys and public addresses means trust is placed instead on the mathematics of cryptography and how well you can secure your private key. Not your key, not your money. With the trust placed firmly on mathematics, the next step is just the consensus of people and computers to accept, value, and maintain transaction history of information such as the numbers on my bank account. So here, this is all we have is a bunch of computers, all with duplicates or copying a ledger, such as this simplified paper ledger I had. But as long as everyone maintains the exact same one, they can all agree, or a consensus agrees, that this is what the chain of events that has occurred. When a network achieves a secure, uniform, agreed upon consensus of one single ledger of events, or a sequence of events, then the ledger can be viewed as being everywhere, since any computer in the network has a copy, such as this. Yet at the same time nowhere, since removing any one computer doesn't remove the ledger from the rest of the network. So you can remove this computer, just this whole section, cut it off. There's still going to be a consensus, so you can just go and connect to it. So in other words, you haven't removed it, but it's everywhere. Every single one can see it. And if they're a part of the nodes that maintain it, they can all have that in their system or in their computer. Yeah, so it's everywhere and nowhere. I'll put that in bold. So it's everywhere and nowhere, since, yeah. So it's everywhere since any computer in the network. It's everywhere since any computer in the network has a copy, and nowhere since removing any one computer doesn't remove the ledger from the rest of the network. So it's everywhere and nowhere. So you can have it, this is pretty cool visualization. So here's my ledger, and all these computers are trusting it, and that's my $1 million. So a network of computers upholding a single ledger is akin to a group of people upholding a single set of laws that you're going to follow. If you want to be part of this, you got to follow that rules, whether it's proof of stake, proof of work, and so on. In other words, a decentralized ledger on the interconnected giant Earth computer is just a digital country and is as open, closed, borderless, or bordered as any other physical country. So these are pretty much like countries, and how they interact or connect is just like how countries are. Just as conflicts, mergers, trade agreements, and war arise between countries, the same will inevitably arise in the digital countries that are rising out of the ashes of the old world being currently set on fire. Stay tuned for part 2. Anyways, that's all for today. It's a pretty cool network there. And hopefully you enjoy this just pretty interesting discussion on blockchain and what it means and so on. I wanted to put a video kind of like this, which is a more overview discussion of just the entire purpose of it. And again, it's to remove the banks. In other words, remove ownership of by a central authority. So now you actually can own the money in your bank, which is just a private key that you store under your bed. So you store the private key, and then that is the only way you can change it. That with the current current public mathematics and technology available. Anyways, that is all for today. Thanks for watching. I'm just scroll all the way up, and yeah, these are digital boxes and so on, and some economics 101. So this is the entire idea was this: how do I give someone digital cash, digital numbers, digital paper for an item that I want? And how can I make sure that item is not copied and pastable and so on? Anyways, that is all. Let's see how much more. This is some pretty cool stuff, actually. This is a plumbing network. The water plumbing is pretty cool in of itself. But now you got the light plumbing, which is absolutely fascinating. These are a lot of light just traveling everywhere. And yeah, that's the internet. It's just a bunch of little pulses of light. And yeah, just going through fiber optics. Anyways, that is all for today, and yeah, I'll do part 2 later time. Part 2 will be more on the philosophical view of just technology and what it means and how we got from the printing press to where we are right here. Anyways, that is all for today. Thanks for watching, and yeah, like always, yeah, first you can also download this via the notes on the Hive blockchain. Link in the description below. Anyways, thanks for watching. Stay tuned for another Math Easy solution.